Okay, ladies and gentlemen, we're going to talk about our next topic from section 8.2. 8.2 is a section dedicated to using calculus to find volumes of geometric figures. And one family of shapes that we're going to explore is called solids of revolution. Very exciting title, revolution. And sad to say, not that kind of revolution, huh? There's Napoleon. No, we're going to talk about math revolutions. And let me show you what that looks like here in this video. What we have here is just some random graph here, y equals f of x. And you're going to see the bottom of this graph fill in here. And to the right, we have a three-dimensional view of the same graph. I just want to point out that you can see the x-axis in both of these graphs. The x-axis in the graph on the left is right here, and that matches up with the x-axis right there. Okay, so we have two different views of the same thing. Let's get rid of those graphs. There we go. So let's continue our animation here, and what we're going to do, well, before I tell you what we're going to do, I should point out that what we have so far is an integral. We have an area underneath a graph, a two-dimensional area. What we're going to do is take that two-dimensional area, rotate it around the x-axis to create a three-dimensional volume. Let's take a look at what that looks like. So here we go. This thing's starting to rotate towards us, and you can see a little better what's happening in the picture on the right. We end up with this kind of shape. It looks like maybe a funny hat with a pointy top or something like that. Now, if you look at the back of a geometry book, there's not going to be a formula for funny hats with pointy tops. You know, it's not like one of our main formulas that we learned back in the day, like finding the area of a rectangle. But we can use calculus to take on areas and volumes of all sorts of weird shapes that we otherwise wouldn't really know how to deal with. So I would like to start with example 3 from the book. This is on page 380. And let me just read it for you. It says, find the volume of a solid of revolution obtained by rotating the first quadrant region S bounded by the curve y equals x squared and the lines x equals 1 and x equals 2 about the x-axis. Alright, that's wordy. Here's what they said. Okay, so we're trying to rotate a region called S. So let me show you what S is going to look like. S, let's pick this color. I like this color. So we're going to bound the graph x squared. This happens to be a little chunk of the graph y equals x squared. It's just a little piece of the parabola, and it is the piece of the parabola found between x equals 1, which is right here, and x equals 2, which is right here. And let me read the problem one last time, or at least part of it. It says, find the volume of a solid of revolution obtained by rotating the first quadrant region S. So what in the world does first quadrant region S mean? Well, the first quadrant is just the space defined by the upper right portion of any graph, above the x-axis and to the right of the y-axis. So what they're saying is, we're going to bound a shape, an area, by the vertical lines x equals 1 on the left side, x equals 2 on the right side, the x-axis on the bottom, and then the graph y equals x squared on top. So this is the shape we're going to rotate around the x-axis, and this website's going to do this for us. So let me see if I can do this real quick. There we go. Let's get rid of everything we had there before, and let's rotate this thing. So here we go. It's rotating. From this angle, we can really see what's happening there. It's just kind of showing us the shell of this shape. We can kind of look at it from different angles. You can see how any cross section of this is going to be a circle. This is definitely a circular shape. Anything created by a rotation like this is always going to be a circular shape with circle cross sections. Here's a profile view of this thing from the side. So in this picture, the inside of it looks empty, but we're going to imagine that this is kind of a solid figure filled in, and we are going to find the volume of it. So let's do that. Where to go? There we are. Alright, so let's take a look at this. There's Napoleon again. See you, buddy. Here is the shape. Alright, so let's take a look. What is this? Here we go. So here is what we're dealing with. This is the vertical line x equals 1. This is the vertical line x equals 2. And this is the graph y equals x squared. I'm going to go ahead and just continue it just so you can see the rest of the parabola. We are only dealing with one little piece of the parabola, but that's usually what it looks like right there. And then the x-axis, you can see. This is a shape made of circles, so we are going to accumulate areas of circles using an integral, an accumulation function from 1 to 2. So let's just pick let's take a look at a few specific circles. So in purple. Here, for example, is like the first circle made by this rotation. This circle has a certain radius. The radius is the distance from the middle of the circle to the top. Well, that distance is the distance from the x-axis to the red graph. The red graph is x squared. So this distance is defined by f of 1. That radius is 1 squared, which is equal to 1. Consider also the very outside circle here. So this circle also has an area. The area is determined by a radius. This radius is going to be much larger, but this is still the distance from the x-axis to the graph. This radius is defined by f of 2, which is 4. So the first radius is just a little guy, radius of 1. The middle radius is a radius of 4. Some random circle in the middle is going to have a radius of f of x. I'm just going to call this radius f of x, which is, of course, just x squared. So I'm actually going to erase this and just say the distance from the middle to that spot is x squared. The area of that random circle in the middle then is pi times the radius, that's the radius, squared. Pi r squared. There it is. And we do this with respect to x. Now it just becomes a regular old integration problem. I bring the pi out. I'm doing this from 1 to 2. X squared squared is x to the 4th. This is a pretty straightforward reverse power rule. Keep the pi there. Bump up the exponent. Over 5 dx. 2 to the 5th is what? 32. 2, 4, 8, 16, 32. Yes, that's exactly what it is. It's 32. So we get 32 fifths. When we plug a 1 in, I should have put that in there, from 1 to 2. Can't forget that. From 1 to 2. There we go. So this is the first fundamental theorem of calculus. When we plug a 1 in, we get 1/5. Our final answer then is 31/5 pi units cubed. You can confirm this with the book. Yes, they actually write it in the book as 31 pi over 5 units cubed. Clearly that is the same thing. Any of these rotations are going to have this general approach where we are accumulating a series of circles, and these circles are always going to be pi r squared. So that's the first example. Stay tuned for the next installment where we take on trickier types of shapes.